Classical and Quantum Statistical Physics seminar. Today our speaker is Dr. Isabel Sainz Abascal. She started her study as a mathematician. She did her licenciatura in mathematics in 1999, and then she shifted to physics. She did her doctoral degree and master degree with Andrei Klimov, with Dr. Andrei Klimov. He finished his master degree in 2005. Then he went for a postdoc in Stockholm, and then she came back here as a professor investigator. She is now the coordinator of our doctoral degree. So today her talk is on discrete phase space, MUBs, and discrete Wigner functions.
Thank you. Thank you. Okay. Okay, it's not a seminar. I mean, it's like a review about this. I chose this subject because I have recently worked on that, and we will see what is this Wigner function. Okay, in long time ago, like 90 years ago, two physicists tried to explain quantum mechanics with statistical physics. And so they tried to convert operators and states, and instead working with operator and state, they tried to describe quantum mechanics with real functions in phase space, as one usually does for statistical physics. And it is well behaved. They can find that they can describe the dynamics, the states, everything was working well, but the Wigner function, I mean, now is called Wigner function, have some negative values. So they try to see the quantum states as distributions in phase space, like X and T. And the distribution is, the integral is 1 and all these things, but it has negative values. So it's like about the history of Wigner function. After that, I mean, long time after that, I think mathematical physicist Hudson find a theorem, and the theorem say that the only states that are non-negative in the phase space for continuous variable is like Gaussian states. And also the mixture, the statistical mixture of Gaussian states. So I mean, what is the importance of the Hudson's theorem is that the states with positive Wigner function is not like quantum. It cannot be used for quantum computation or quantum entanglement distillation. So it characterizes some quantum systems that do not preserve the quantum characteristics that are useful for quantum information. But everything was described for continuous variable. But some time ago, like in that could be 89, 1987, something like this, like, I don't know, 40 years ago, someone say like, okay, let's go for continuous variable to discrete systems, like the spin 1/2, spin 1, and then they try to convert the characteristics of the phase space in a discrete grid. The grid is like n by n points, where n is the dimension of the quantum system. And what is important? The important thing is that this plane should be an affine plane. What means an affine plane is like a Euclidean space, like two parallel lines do not cross, and two lines that are not parallel intersect in only one point. This is very, very important. So they can preserve all the, they can preserve all the, the, no, no, hasta en español perdí la palabra. Properties, yes, las propiedades. Yes, the properties of the phase space. This is also related with a very old, everything is very old, work from Schwinger. Schwinger tried to describe discrete quantum systems with some variables like x and zeta. In 2 dimensions is like Pauli matrices. And what is important here is important that these operators should behave more or less like these operators. But of course, they do not commute. I mean, the commutator is y. But they preserve some kind of things, like all the eigenstates of this operator is very different, like these eigenstates. And one can form several of these operators and describe a complete, describe any operator with these operators. Like if we have a n dimension, we have all possibilities. And so on. So we have n squared operators, and these operators is an operational basis. What does it mean? That any operator can be written in terms of this. Okay. So this is like the discrete phase space. A discrete phase space is defined like this. We can define some lines. This is for dimension 3, like for a Q3. And we have, every line have 3 points. If the dimension of the quantum system is 3, if it's 4, it has 4 points, and so on. So every line has n points, and each point is contained all in n plus 1 lines. We have n square points, this we understand. And we use some notation, and the notation is that all the lines that are crossing the origin, we will call rays. But for every ray, we have some striation. And the striation are the parallel lines that are different to some ray. For example, if we have in dimension 3, we have 1, 2, 3. We have some rays and some striation. Like this is one ray, and this is one striation. This is the striation of this ray. And we have another ray. And we have the striation is like this, with this, and like this, with this, for example. This is the same line, and this is the same line. Yes? So we have n plus 1 striation, and this is very important. Because we can construct this kind of affine plane if and only if the dimension is a power of a prime power. It's like, it can be like 2, 4, 8, 3, 9, 27. If we have some other number like 6, a composite number, we cannot have an affine plane. And this is very, very important for MUBs construction. So, how this is related with mutually unbiased bases? Why are they important? Mutually unbiased bases, MUBs, were firstly used for quantum state determination. So, we try to find some state of a quantum system, n-dimensional quantum system, and we can have a very easy reconstruction formula that is this one. These probabilities are the probabilities of finding this state, rho, in this state of this basis. So for this reconstruction, we can find only for MUBs. If we have a state of dimension n, it's a density matrix that is Hermitian and is normalized. So it is a matrix n by n. So that is Hermitian, and its trace is 1. So we need to determine n squared minus 1 parameters. And the best way to determine it is with these MUBs. But these MUBs only exist for a prime power number. Why? Because the discrete phase space is an affine plane only for this kind of dimensions. What is important in these MUBs, that if we have two bases that are different, the basis is this index. For any element k, kappa prima, we have the same value. So the inner product of any two elements of different bases is the same as is 1 over the dimension. This is the best way to find a quantum state because the information that we obtain is maximized. The measurements that we need to do to measure the state is minimized, and the statistical error is minimized as well. So it's the best way to find a state. How this is related with the discrete phase space? Okay. So if we have our discrete phase space, to every striation, it corresponds a basis. So this is the basis for these operators is like 0, 1, 2, 3, the computational basis. The vertical basis, this is are the eigenvectors of X. That is the Fourier transform of this operator. And we have another n minus 1 striations that correspond to the rest of the basis. It's okay. So I don't want to talk about a lot of this mathematics because I see a lot of undergraduate students. So I prefer to do some kind of drawings in the whiteboard. So, which is the reason that we can have this only for prime power dimensions? And the reason is that for prime power dimensions, we have something that is called a Galois field. So it is a field like the real numbers, like complex numbers. And that is very important. If we have other dimensions, we don't have a field. We have a ring. And in rings, we cannot have an affine plane. Okay, so the construction is just as I told you. Okay, there are... Pablo.
But this is a particular discretization of phase space for having something like, something that can fit in a thin plane, right? Because in principle you could discretize in any way you want, maybe? Or
Yes, yes. We have do the same for non-prime numbers.
Mm-hmm.
And we are not working in the field, but we are working in the Galois ring. But the measurements are not minimized. It's redundant.
Okay, so this is basically for MUBs. This is the best way for, in the context of MUBs.
Yes, and Wigner function.
Yeah.
Yes, it's in the context of MUBs and Wigner function. Yeah. We can also construct some kind of MUBs for non-prime powers, but once stop working on the Galois field and start to working or in the Galois ring or with the Chinese remainder theorem. This is also possible. There are some works that the people is working in dimension, 6, and is working with two fields and using the Chinese remainder theorem. And the MUBs are not really MUBs, and there are more than they're necessary, and not all them fulfill this relation, but very similar relations. It's very beautiful. Mathematically, it's really, really beautiful. But the thing is that the statistical error is also minimized, but we have redundant information. So to be not redundant, it should be an affine plane. Yeah. Okay. There are several ways of constructing the MUBs. In our group, we are working with a very established way. And I will explain you how do we construct it. So we start with the operators of the computational basis. That is, we start with all these lines. And we say, okay, we will say that this is the 0. We can say that is 1 or 2, or we have all this liberty, all this freedom So we start with this with 0, and then we apply operator x that is shifting it. And then we construct from 0, 1, 2, 3, etc. Of course, these elements are just the Fourier transform. So there is nothing to do, just the Fourier transform. How do we construct the rest of the bases? So we understand that we can divide this grid with striations that are straight lines. So what we do is applying a rotation in this this axis. So we rotate how much we can rotate all the field. This is 0, and then we have all the elements of the field that here is represented with this mu. So we apply a rotation, and for every mu, we will construct another basis. Okay. Creo que me salté una. Ah, no, ahí está. Okay. So we want to transform all these operators, that is a set of commuting operators that are defining a basis, to another set of commuting operators. And this operator, this is very important for the last of the presentation, that these phases should fulfill this equation. This is the character of the group. Okay, so this is like the construction. We apply, then we take this state and we rotate. And then for the rest of the striation, we apply operator x, that is shifting. But I don't know if you were talking about this. It's not the only way. So we always start with the computational basis, with these operators. We can apply not a rotation, but a unitary operation. And this unitary operation could give not a straight line, but it could give like a curve. Even it could be some degenerate curve, something like this. This is another way to construct the mutually-based basis. And they fulfill the equation that is very, very similar that the other one. Is basically the same one. What is important? When the field is not 2 or a power of 2, we find a solution, and the solution is very easy to find. Is this one? But when the field is like 2, I mean, if we only have 2 elements, 2 is equal 0. So this is not existing. And it doesn't have a solution for 2 inside the field. So one must move outside the field. There are different solutions for this equation, for this one. And this is physically very, very important. Okay, this is MUBs. There's some questions about MUBs. Do you have questions? No? Everything is fine. Okay, so Wigner function. The Wigner function, we will try to describe all these discrete quantum systems like in a plane, a phase space. What will we use? We will use some kernel, and this kernel is what helps us from moving from operators to functions in this space and back. And the functions, W in this phase space, we can move to operators. So it's a mapping that is going from the operators to the phase space and from the phase space to operators.
This is discrete function also, Wigner function.
Yes, it's discrete. Yes. So there are two ways basically about constructing Wigner functions. One is like following the recipe of Wigner for the continuous variable systems. So we start with a displacement operator and these kind of things. And the other one is like with MUBs. Surprisingly, is exactly the same. Is exactly the same result of Wigner if we work with one or another. I mean, it's equivalent. So in our group, we construct our kernel like, okay. So as I told you, we assign to every line in the discrete phase space a state, but it's not real state. It's the projector of the state. And here we have another state, like how do we construct this kernel? So we take a point. This point is alpha, beta, alpha, beta. And then we zoom every line that is going through this point. This expression is just that. We are zooming all these lines in this point, and we have the Wigner function. So, which properties it has? It is normalized, is orthogonal, and is covariant under displacement operators. So we can start with all the rays and then displace, and we can get all the points in the phase space for the kernel. And it should have another property that is very important, and it is since the very beginning in the Wigner or the Mojal work, and is that if, okay, we construct a kernel here, and if we find the Wigner function in that point, I mean, remember that every line is related, we say, with a projector. If we zoom all the Wigner functions of the state in this line, it should give us the probability. The probability that is related with this line, because this line is related with some state. Okay, what is new? All that I told you is very old. Is old or very old. What is new? The new thing is that we find something that is somehow known, somehow. I mean, it's not reported, but then we start to thinking about that, and we say, okay, it was known. It was known, but it was not expressed in this way. And what did we find? We find that we can construct a Wigner function with some partition. We have the phase space, we have the grid, we have the points, and we say, okay, let's consider this curve and this curve. I mean, the thing is that we are partitioning the phase space in different ways, in moves, different kind of moves. But we have another kind of partition, like this one. What is new? It's new that if I construct the Wigner function, like in the green partition, and then I measure in the black partition, the tomographic condition is still working. Yes, that is strange if we're thinking in moves. But if we are thinking in Wigner function, it's not strange. But this is only true for dimension not even. I mean, only for odd dimension. And this, of course, is related with some very new results that are that the non-negativity of the Wigner function is a signature of non-contextuality. But this is true only for odd dimension, and this is new for, I mean, 2-3 years ago. And of course, it's related with this one, this, because we can take not any curve in a move, but we can take any curve in the phase space, I mean endpoints, which points, whatever you want, and this tomographic condition will be satisfied for every endpoint that you can find. I mean, you can choose endpoints, and this is true for odd dimensions. However, for for even dimensions, you can forget local. This is not true. Why this is not true? This is not true because this equation, the equation that I showed you when we were constructing the moves, it doesn't have a unique solution. So we can move from the Galois field to solve this equation. There are several ways of solving this, but we were using this one. Okay, we fix some elements of the field, and we just take the square root. But we have some freedom in this election of the sign. And the thing is that if we fix one thing, it's like we fix, I don't know really what we're fixing, if we're fixing the thing. So I really don't understand what we are fixing. I mean, mathematically I understand, but physically I don't understand.
So this tomography condition works fine in enough dimensions. In even dimensions, then it doesn't, and this is related to the negativity of the Wigner function. as was mentioned before, or not?
Yes, of course. So the non-negativity of the Wigner function is not a signature of non-contextuality. I mean, you can have non-contextual system or state, but the Wigner function is still negative for even dimensions.
What is non-contextuality?
Good. It's not well described by a hidden variable model.
It would be contextual, then it could be described by a hidden variable.
Yes.
Where contextual,
Yes.
then it could be described by a hidden
Yes.
variable. If it's non-contextual, then it cannot.
Yes. It's not well described. And of course, if we
the local or non-local physics in that context.
no, it doesn't matter if it's local or non-local. Think about that. So we have this reconstruction formula, this one. So if I can take this in, I mean, this is of course associated with this. But if I can measure this with any, I mean, I can fix some projectors and I can measure. But then from this measurement, I can find some probabilities. So we can describe it with a hidden variable model that is the probabilities that I can find. I mean, I can fix the basis, and for this basis, I can find any probability. So it's like a hidden variable model. Of course, we should do some convolution of operators, but I don't want to. Okay, but the problem here is the to find the right thing. I don't know what does it mean physically. I mean, it's just a phase. It's like the phase. This is like the phase of the displacement operator of the Wigner function. But I don't know what does it mean. If it means that we have a different setup, I don't think so because we have the same commuting operators. But I don't know how much the phases can contribute to that. But what we find? So we have evidence that for different, if we can find some assignation from the beginning, every curve can be described for even dimensions. So we have the freedom to choose here the sign, and we have a curve. What curve? Whatever you want. Okay, we have this curve. We have this curve. So there exists some assignment of the signs for which this curve is also a positive Wigner function. So, and I don't know if you understand.
Any questions?
No. Everything.
I mean, get the MUBs by rotating the computational basis, right? Or the what's it called, striation,
The
or
striation.
the horizontal one.
Yes.
So you can rotate it by which, or what is the rule for rotating it? I mean,
The rule.
how many rotations do you have?
In all the field.
Yeah.
I mean, if you have a Galois field, you have this number of elements. You can rotate this, except this one. That is the zero.
Try to imagine this geometrically, right? So you have the horizontal line and you move, say you take the origin and the next point would be the, say, n points to the left and one to the top.
Uh-huh.
But then what would be the next possibility would be n-1 steps to the right, sorry, and one. Or are there n squared rotations possible? That
No.
seems too much for me.
P at n rotation
Why P of n?
is the number of elements of the Galois field.
So P of n is the number of points in one dimension.
Yes,
one
yes, yes.
direction.
So I mean, it's the elements of the Galois field. So it's the number of. So one is this one that is the original, and then we can have like
What would be the
one
next one?
and one, like this one, and all the striations.
Yeah.
And then we can have like 1 and 2, and 1 and 2, and 1 and 2. This is the other line. So the other line is this one.
Almost. Right?
Almost, yes. Uno, dos, this one. One,
Oh, this is already two.
this. And one, and this. Yes.
So,
Something like this.
Yeah.
This is one line. I mean,
Yeah.
this line is another rotation. It's another line. Because it's like cyclic. Of course, it's cyclic.
Then you know that you cover everything.
Yes, of course. You cover everything. You cover everything. And this is also related that is an affine plane. Yes.
So you have P to the n plus 1 orthonormally based loops.
Yes. Mm-hmm. So, something else?
We have n plus 1
Race.
race in the whole discrete phase space. And you already explained that we needed to make the mapping of the state that we want to measure. I don't know if that's the right word to use here. In order to know the probabilities of a line, just one line. In order to know the whole mapping of the whole phase, we need to make this measurement point by point, or is there an
The measurement is line by line.
line by line? Okay.
Yes. Every line corresponds to one state, to one projector.
Okay.
So it's line by line.
So this measurement is, if I can say it right, is made. You choose one point, and I need to know all the lines that pass through this point in order to make this measurement.
No, in order to construct
In order to
the
construct.
kernel.
Okay.
That is the mapping from the phase space to the I don't know, to operate from between operators. This is between operators and real functions. Yes, you need to zoom all the lines in some partition. Which partition? What you want. It could be with striations, that is the easiest, or it could be with another curves.
I have a question related to this. So if you select any different move, then you can construct different kernels, and different kernels give you different Wigner functions.
No, that's very. I was not that clear. That clear. This is exactly the same kernel, exactly the same for odd dimension. Oh, I don't find it. It's exactly the same. And this is related that the solution is unique.
Yeah.
So it's exactly the same kernel
Okay.
for odd dimension, but not for even. And for even dimension, we cannot find a unique solution.
I have a question about the definition of the kernel in the other kernel. So we define part of the kernel is this state F.
No, the kernel is this one.
And
F is an operator, a density matrix, whatever you want. And the kernel, this one, W, is what is mapping you from operators, F, to real functions, and from real functions to operators.
And why is it that we can define the Wigner function in terms of the operator and the operator in terms of the Wigner function?
That's the whole point, that you can find some operator. I mean, it's not the only one, because Wigner function is not the only quasi-distribution, but it's the only one that is hermetic and self-dual. This is very important, that is self-dual. What does it mean? That we use the same from going from operators to functions, and from functions to operators, we use the same one. Mm-hmm.
This operator is related to the observable that we want to measure.
Yes, and also with the state. It could be both, the state and the, I mean, it's any operator. It's an observable, it's an state.
Another question about the construction of the base, the moves and the corresponding lines of each move. You mentioned that in order to create the new bases, you need to make the rotation from the computational bases, right?
It's not the only way.
Okay,
It's
one of the ways.
Yes.
One of the ways
Yes.
that you, well, the one that you're currently working
Yes.
on. My question is, how can I create the whole situation? Okay, I know the computational basis and I rotate it. How can I make the connector of the
with X operator.
Just the X operator?
Yes, because X operator is like the shift operator. So it's shifting. So we have this is like 0. And then we apply X, and we are getting 1.
Yeah.
And then we apply x2 or x squared, and we have 2. And it's the same like this. We have this one, and then we apply x, and we move, we shift it
Okay.
to this.
Okay.
This is expressed here. So we rotate it, and we obtain the zero element of the basis mu, and then we apply x, and we obtain the next element.
What is the use then of the C? The zeta?
Zeta. It is the computational basis. We start from there.
Okay, that's the origin, and
Yes.
we go.
Our construction is always from there, from zeta, or theta. Even here, that is not a rotation, but it's a unitary operation. We start from theta. That is from the computational basis.
I have a question. For example, in the case of one qubit, you have the computational basis 0 and 1. And for example, a different move for one qubit is the superposition, right? The 0 plus 1.
Yes, the y.
And with the phase, right? Then you apply, then not an x operation, you apply an Hadamard operation. That's
Yes, but Hadamard is a rotation. It's exactly the rotation. So it's like it's sigma zeta and sigma y, and sigma x is the Fourier transform.
So, do you know if there is some sort of mapping from this Wigner discrete function to some continuous Wigner function, even for these discrete phase spaces? Because I saw once that there is this Wigner orbital angular orbital momentum, and then you can have a description in a discrete way and in a continuous way.
Yes.
This is impossible for this kind of situations.
I really don't know if you can move to the sphere, or
Yeah, whatever.
it's a kind of a sphere, I think. I really don't know if it is possible, but maybe Jose Luis can tell you.
okay.
Any more questions?
No, not this Jose Luis. I don't know. But Jose Luis Romero, by sure,
Yeah.
because he have worked with both.
Yeah.
Okay, if there is no more questions, then we just thank the speaker once more.
Thank you very much.
I'm sorry.
Okay.